All right. Good morning, everyone. Let's get started with today's class. So last class, we basically we finished our intro to R. So if just I guess here in Athens, it's easy for me to see you. Can you raise your hand if this is the first time that you're using R, or maybe that you're not quite as familiar with R? Can you raise your hand just so I have some idea? Okay. So a few people here. Awesome. All right, so that helps me as well just to understand the pace that I'm going. If I'm tr- I try to explain things as I go, but if I'm not making sense, please feel free to raise your hand and let me know, and we can answer any questions at any point. All right, so we finished our intro to R. We talked about reproducibility and some tools that we can use for reproducibility. And today we're going to do our data wrangling exercise. I would still consider this somewhat intro to R. It's not going to be like R like what we're talking about in the first part of it, but it's going to be a very important skill that maybe you're already developing. If you're not, at least you're going to get started with that in R. And I think it's really, I mean, a lot of my projects, all of my projects all have data wrangling steps to some extent. Some are very light, some are very complex, and the whole project may basically be data wrangling just because of the need that it may have. So data wrangling is going to be present in everything you do, in every project you do to some extent. And normally in data science projects, more machine learning types of projects, data wrangling can be, up to 50% of what you do may be data wrangling. So it's a very important part of what we do, how we work with data. And I want to show you some of the functions that at least I use the most. They are not the only functions. There are many, many functions for data wrangling. I want to show you some that at least in my experience, I use most frequently. All right, so I'm gonna go here to the folder of the course. I'm gonna navigate there. You can do that on your side as well. So if you remember, I shared with you some files on the 2025 DSA. This is the last time you're going to manually download it. On our next class period, on next Tuesday, we're going to be talking about Git and GitHub and how to get your local Git connected to a GitHub repo. And that way it's going to be a lot easier to sync files from the GitHub to your local computer once I upload them to GitHub. All right, so I asked you to manually download for the last time that 2025 DSA main, which at this point, well, I guess before I go in there and show you what you should be seeing, I want to ask you for us to create here the structure of the project we're going to be working with today, right? So you should be on the main folder of this course, like I am. So you should be seeing 01 intro. Maybe you moved your 2025 DSA main to this folder, and I have a couple of other folders you don't have yet, or you're not going to have. So if you're at this level, let's come here and create a new folder called 02 underscore wrangling. This is going to be our second exercise. To the best of my capacity, I try to be mindful of how I name everything, like folder names, file names, project names, to follow those guidelines that I share with you. Sometimes I may forget, and you may catch me with not naming things the best way, but I try that to be mindful of my naming scheme. So we're going to be developing here 02 wrangling. So coming after the 01 intro, we talked about left padding with zeros. We're doing all that here. So if you come inside 02 wrangling, if you remember, we have 3 minimum subfolders we create, right? Can somebody help me with the first one? Data, right? Data is the first, is one of them, doesn't have to be the first one we type here, but there's one of them. What is the second one? Code. What was the last one? Output, right? Thank you, everyone. Exactly. So again, this is a recommendation from my side. This is the minimum number of subfolders I create to keep myself organized. You could create more if you need to. It's very flexible, right? It's just creating subfolders. But this is the three minimum that I recommend you always use for projects to keep yourself organized. Oops. All right, so now that we created zero to wrangling, and inside of zero to wrangling, we created all of our subfolders. I want to go back to the main folder for this class where we see, or at least that's where I have 2025 DSA. If you have it there as well, it's going to work similarly to you. If you have this 2025 DSA elsewhere, you're just going to have to adapt what I do next. So if you remember, and I just want to call your attention again to this, I do not want you to work with the files from 2025 DSA right off that folder. I don't want you to go inside 2025 DSA and just double click that script and launch it. I do not want you to do that. Think of 2025 DSA as a folder that I use to share my files with you in a way that if you completely delete 2025 DSA from your computer, you're not going to lose anything because you can just download the version I share with you, meaning you did not make any changes yourself to the files inside 2025 DSA. That's the mindset I want you to have. So let's go inside 2025 DSA. I have a few more folders than you at this point, but there are two files I share with you here. The first one is going to be inside 03 data. So if you have the latest version of this repo, you should be seeing 01 soybeans XLSX. Let's copy this. Remember, we're just copying and then pasting in our working folder. So copy this data frame, get outside of 03 data, get outside of 2025 DSA. You should be back to the main folder of this course. You go inside 02 wrangling, go inside data, and paste this data frame. Okay, I know I went a little bit fast. Let me just quickly show that again. I was inside 2025 DSA. I was inside 03 data. I copied the 01 soybeans. I got outside 03 data. I got outside 2025 DSA. Now I'm back to the main folder of the course. I went inside 02 wrangling, inside data, and pasted this data frame there. All right, so now I want to get outside of data, get outside of 02 wrangling, and be at the main folder of the course again. Because now we're going to do the same thing, but for the script. So I shared a partial script with you that we're going to be developing today. So go inside 2025 DSA, go inside 04 class code. There's going to be a 0114 data wrangling partial.rmd. So you copy that, get outside of 04 class code, get outside 2025 DSA, should be back on the main folder of the course, go inside 02 wrangling, go inside code, and paste this partial folder there. So at this stage, you should have, I'm just gonna unfold here my structure. So if you are inside 02 wrangling, you should have a partial script under code, and you should have the soybeans data frame under data. And at this point, nothing under output, because that's something we're going to produce afterwards. All right, anyone got lost? Anyone needs help? Anyone needs more time to do this?
Bastos,
Yes.
I think I was having issues with my computer. I tried to create a new folder. Anytime I click new folder, like nothing pops up. This is the first time it's happening. So I don't know if I need to restart my computer also.
So sorry, I think I missed like what happened. What was the problem?
Yeah, I was struggling to create a new folder. Like
Mhm.
when I create the new folder, nothing pops up. And when I rename a folder, it does not rename. And this is the first time it's happening to me on my computer. So maybe I might need to restart it. Let's see.
I see. Well, Swabir, if you want to try to restart that and let me know if you can catch up, because the next step here, we're going to create an RStudio project, and then I'm going to be talking about what that is. And so you may have a few minutes to try to catch up. So let me know how that goes.
Okay.
All right. Anyone else needing more time, having issues, having questions? All right. I don't hear anything, so I'm going to keep moving. So the next thing I want to do here, which we're going to be doing every single time that we create a new project, is to use RStudio projects. I briefly talked about this in our reproducibility lecture, but I want to show you now what that is and why it is such a simple yet powerful tool for us to be able to manage different projects and different files within those projects. So I'm going to launch here any RStudio window on my side. You can do that on your side if you want as well. If you have not been using RStudio projects, you will most likely, let me just give it a second to launch, and then I'll show you a few things here. So if you have not been using RStudio projects, you probably have here, well, let me close this so we can have a similar view. You're probably seeing project none, right, on the top right, which if you're not using RStudio projects, that's the default view. So what happens here is, let's say I have a project that I have already collected data for, I'm running some analysis, and I have a script. If I launch that script, it's going to pop up here, right? So let's say it is a script that I'm doing for corn yield analysis. All right, and then I have a student from my team comes to me and says, hey, I have this data, I have this script here, I'm having issues with it, can you help me with that? And it's a different script from a different project altogether. And I simply just double click on that script, it pops up on the same RStudio interface I'm looking at. If you start doing that, you're going to run into issues at some point, because you're going to have objects that are going to have the same name across different scripts, and they have nothing to do with themselves. So let's say my data frame, I'm importing that into an object I'm calling df. And maybe on your script, you also have a data frame called df. However, so that's a competing name on the same environment from two different projects that should not be together. They don't belong with the same analysis. So RStudio projects is going to be a way to help us to create these containers, in the sense of, like, you have a full analysis contained here that's completely separate from this other one, and so on, all within RStudio. So an example, if you don't have a project, it just says project none. You know that because it's always going to say project none on the top right. If I click here, I have been using a lot of RStudio projects. So each one of these names showing up here are a separate RStudio project that or at least the latest ones I've been opening, they're showing up here. So I just want to give you a quick example. I'm going to launch this one that is called design. So this is a study that we are designing that's going to be conducted this year. So you can see that it has, so now the name on the top there, it says design. So I know I am in that specific project. The name itself doesn't matter, but it's not project none as it was before. One really cool thing is that once you start using RStudio projects, every time you launch that project, the whole view that you're seeing on RStudio is focused on that specific folder where those files live. So if I come here on the Files tab and I click on this R blue button, it takes me to the home folder of this project, which is just this. It's not a very well organized project because I really just have a Quarto script. So it's like R Markdown. And I have a study layout that I produced to share with to put in a presentation, for example. But so a couple of things that are really nice here. Let me see if this is a good example. This may not be the best example. Let me launch another one here. Yeah, this one is a good example. So the usefulness of it, again, is the folder where you create that RStudio project is going to be the home folder that pops up when you launch RStudio with that specific project. So the benefit of it is all of your scripts related to, so here, this is a bad example. So this project is called Management Zone. We're creating management zones in my other class. So I have code, data, and output. I have an rproj icon at the same level as code, data, and output, which represents that RStudio project. And if I click on this R blue button, it always takes me to the home folder of the project. So we can see code, data, and output. If I go inside code, I have a couple of scripts going back to the home folder of this project. If I go inside data, I have a few data frames as well. And then if I go on output, I have all the outputs related to this project. So it focuses your view on those files only, and that helps you to keep things separated. So very, very useful. Another thing that's really useful here is that any programming language by default, it's going to, whenever you try to import files, is going to use the root of your computer as the starting point of that path of the file. And that is not reproducible, right? Because my root of my computer is not the same as any of you. Like it's going to be something like users, lmbastos, documents, something like that, right? Mine is completely different from yours. So if I share a script that I developed using an absolute path with any of you, you're going to for sure have to edit that path because it's not going to match yours. So unreproducible. The solution to that is to use relative paths. Relative path is going to be a path that's relative to a higher level in your system. In this case, the relative path that we use within an RStudio project is going to be wherever that our project is. So that is your starting point. So if I share this project with you and you have the same folder, does not matter where in your computer you save that folder, your relative path is always starting on the same place, which therefore makes it reproducible. So this is really useful when we're importing data, which we're always going to be importing data. And when we're exporting data as well, we need to determine what is the path that you want to export something, and relative paths help you with that. And our RStudio projects use relative paths by default. So a very useful, two very useful components. Just to give you yet another example here. So let's say I'm working on this exercise, I'm doing some analysis, creating some figures for a paper, and then I need to switch to another project. Like, oh, something came up, I have to stop this and do something else related to a different student or a different class or something completely unrelated to what I'm doing right now. You can navigate here on your latest open projects, but here's not going to be a comprehensive list of all the projects you have. I hope that if you do use this tool for your own analysis, you're going to end up with many more RStudio projects than it's going to be able to fit here. So one way that you can go to that project. So I'm going to open this file here on my file viewer on my operating system. So let's say I come to this project, I see this rproj icon. If I just double click on that, this is going to launch this project for me in a different RStudio window, completely focus on the files that belong to that analysis, right? So it's really easy to switch between two different unrelated things as long as you use RStudio projects as the backbone of this. Right, so let's say if I wanted, I have to go back to this random forest exercise, which is not related at all to what we're doing at this point. If I open that, it's gonna open that RStudio project instance with a complete different set of scripts, of files, of structure, right? It's a completely different thing. It's a different folder in my computer altogether. So code data and output subfolders are helpful for us to keep track of our files in a project. And then RStudio projects is really useful to manage multiple projects and being able to switch quickly between different ones. All right, so our next step, I just want to close all these projects I opened that you don't have on your side. So we get back to a common place here. So I'm just going to go ahead and launch any RStudio window. It does not have to be, oh, where's my, I think my cursor was taking a break for a while there. So I'm just going to launch any RStudio window. Please do that on your side as well. Does not matter if it's a project or if it says project none. At this point, that's not the main point we're looking for here. Let me close my project and have it show project none so it matches what you see on your side. So every time that we start a new analysis, we're gonna always create folder like 02 wrangling, the subfolders, code data and output, and then an RStudio project inside of that folder. This is gonna be the default behavior for everything we do in this class. And today I'm walking you through very slowly through it. After today, you're gonna have the recording if you need a refresher, and I'm just gonna say, hey, create a folder named like this and move these files in there. And I'll expect you to know that code should go on code under the code folder, data should go into the data folder, and so on. So So, okay, so we created zero to wrangling, we created the three subfolders, and now we're going to create the project at that level. So come here on the top right, click on that project none. We're going to ask to create a new project. Here, all right. So for today only, we're going to use the second option here, which is existing directory. From Tuesday onwards, we're going to use the version control option, which because we're going to be using Git and GitHub for that, but we have not gotten to that point yet. So for today, if you're not using Git, if you're not using GitHub, you're always going to be using the existing directory option here. Here on this window, we want to browse to where we created zero to wrangling. So I'm going to do that on my computer. It's going to be a different place than on yours. So you just need to make sure you navigate to the main folder of the class. So main folder of the class for me is right here. So I'm seeing 01 intro, I'm seeing zero to wrangling and so on. I want to go inside zero to wrangling, and at the level that you see code, data, and output, that's where you want to create your RStudio project. So I don't want you to create RStudio project outside of zero to wrangling. I don't want you to go inside code, data, or output and create there. I want you to be seeing code, data, and output and create at this level. So when you're here, you just click on open and then create project. And then it's going to relaunch RStudio with that project. Now you know you are in that project because it is showing, at least on my side, is showing the folder name where the project was created and a little bit more information about the folder above that. Okay, well, before I keep talking here, was everyone able to do this? Or maybe let me ask the opposite question. Was somebody not able to do this and needs help? All right. I don't hear anything. I'm going to keep moving. Make sure you're following, placing things in the same places that I'm doing, because that's going to be required for you to be able to use the relative paths successfully. If you have done something different from me and you didn't realize yet, you will when we import data. So let me know if you have issues at that point. All right, so a couple of things I want to notice here. Notice that now our files tab is focused on that zero to wrangling folder, right? So if I go inside code here, I should see the partial code that we copied in here. If I go inside data, I should be seeing that data frame. A couple of very useful, I guess, tips that I would tell you as you're starting to work with RStudio projects. One of them is this is the main folder for the project itself. So it's always going to refer to that as the root of the project. If I am navigating through RStudio and I click on data, let's say, or maybe let's say I click on code because I want to launch the code here on the left side. And then I want to go back to the main folder. So I want to see something else. Always look for this RStudio blue button here on the right. If you click on that, it's always going to bring you back to the home view of this project inside RStudio. Okay, so that I always use this as it's very useful button to be aware of. Another thing that I use a lot is maybe you have not found this out yet because you didn't have the need. But sometimes, I'm like, oh, I by accident, I saved a new script on the data folder instead of the code folder. I just want to drag and drop into the right folder. You may be tempted to do that through RStudio. So, we're going to come here, drag and drop this somewhere else. It's not going to work. RStudio does not have that option to drag and drop things inside RStudio. So every time I need to actually move a file myself inside of the RStudio project, I come to the main folder of that project by clicking the R blue button, and then I use this blue engine icon here. If you click on that, it's going to give you an option to show folder in new window. That is going to launch this folder on your operating system, and then you can move as normally as you would, right? So two things I use a lot is the R blue button to get back to the home folder of the project, and then the engine and then show folder in your window if I want to have access to the files to move around, things like that. All right, so last chance, if you were not able to get to this point, to speak up. If I don't hear anything, I'm just going to move on. Right, let's move on. So, okay, so if you're not seeing the main folder of your project, which I think you should, but if you're not, remember our blue button takes you there. We're gonna open in our studio here, navigating on the Files tab, you're gonna open the code folder and launch the partial script that we just moved in here. And then we're gonna be working out of this. All right, so we talked about folder structure, subfolder structure, moving files to the right places, creating our studio projects. And now yet another new concept, if you're new to R. If you're not, you may already be familiar with it, but another new concept here. So what we're looking at right now is a .rmd file. This is an R Markdown file. It's a very popular scripting file within R. And I want to give you a quick tour of it and why we're going to use it and why I think is very useful for coding. So as you can see, the structure looks a little bit different from the .r script that we use on the intro to R, and it is different by design. R Markdown is a type of literate programming scripting file. What do I mean by that? It's a file type that on the same file, scripting file, you're going to mix your text, your narrative, you're going to mix code, and you're going to mix outputs, which I think is so useful. So with .r scripting files, the script itself was just the code, right? If we wanted to write comments like plain language, you would have to have the hashtag symbol before it, and all the outputs would either show on the console if it were a table, or here on the plots tab if it was a plot. Now with our Markdown files, that is different. Now we're going to have basically the concept of a chunk. So this here is a chunk, is one chunk. So you know it is a chunk because, well, it's the background color is a little bit different normally from outside of the chunk. Also, it always starts with 3 apostrophes, and then it has open and closing curly brackets, and then it has some information inside here. The minimum required is the language you're using. So this is saying we're using R. With R Markdown files and Quarto files, which is going to be the next file type we use, you can mix on the same script R and Python if you wish, or Java or other things as well. So this is just specifying what language this chunk is using. This here is the actual code. So you can think of this as being actually the R script. This is what the R script was doing for us, right? Where we have the code here. Now, a few differences here is that, so mixing narrative, code, and outputs. Why is that? So if I am outside of the chunk, which I know I am because I'm not within the fence quotation marks here or apostrophes, I can just type normally. Like I can just type here and no issues will occur when I run the code. This is just plain text. It's called this. You can use Markdown type of coding and syntax here. If you don't know what that is yet, don't worry. But if you know what that is, you can use Markdown outside here. Think of being outside of a chunk is kind of like being in your Word file, right? You can just write normally. Then we have the chunks. When you are inside of a chunk, if you remember from our intro to our class, if you just have a cursor anywhere in a row on the line of code, and you just push Command Return or Control Enter, it only runs that line of code and moves to the next, right? So this we had this option on the R script as well. Now in the chunk, if you want to run the whole chunk at once, it has this play button here. You can just push that and just runs everything at once for you, just this chunk. So none of the other chunks were ran, just this one. If this chunk produced an output, like a plot or a table, that output would show right below the chunk and before the next chunk. So we're really mixing, intertwining in your script your narrative, code, and output. Narrative, code, output, right? And flowing that way, which I think is a very nice way for you to learn and for you to share information as well. A couple more information here about a difference in our markdown from our script is in our markdown, if you are outside, so if you are inside the chunk, think of you are in an R script. That's basically what the chunk is an R script. If you are outside the chunk, like I am here, the hashtag symbol represents heading levels. So as if you were typing working in Word, for example, you had a heading 1, 2, 3, 4, 5, right? So the number of hashtags outside of the chunk represents heading levels. So here, and those heading levels you create outside a chunk show up on your outline. I highly recommend you, if you're using already R Markdown, or even if you're not, but to have a habit of creating your outline in your scripts. I have some scripts that have like, I don't know, 2,000 lines of code, which I don't recommend you create scripts that long. They're really not helpful. I'm trying to avoid that these days. But if you have to, it is a really long script. It's hard for you to navigate in that script if you don't have a good outline. So here we have a very nice outline that helps me when I'm planning this class, but I hope also helps you in case you ever need to go to a specific place of this script and you can just easily navigate with the outline, which is created partially with the heading levels. So something I always do in my scripts, I think is very common practice when you're programming, is you have a setup initial part of your script. For me, that setup normally is loading packages that I need. So every single package I need in this script, I load all those packages in my first chunk, as you're seeing here. And then the next step of my setup is importing data. That's normally how I start my scripts. So here it would be, let's say, if I wanted to be explicit about creating a subheading, or a heading level 2. So this is a heading level 1. If I wanted to create heading level 2 saying, like, this is where I load packages, this is where I import data, I could just type 2 hashtags and say, like loading packages. And then I could come here in the next chunk where we import data and say reading data. And then you can notice how those heading levels appear on my outline as well. So you can use these to keep yourself aware of where you are in your script and also keep your mind organized as far as how you navigate things. You're going to realize that for every script, every analysis we do, even though we may be doing very different analysis, but the overall structure, the overall skeleton of the analysis is going to be very similar. You do a setup where you load your packages, import data. You do data wrangling, you do some EDA, exploratory data analysis. Then you get to modeling, you get to extracting information from the model, creating a table or a plot, and exporting. That is a workflow we're going to see across every exercise we do, even though we're going to be playing with different types of data in different moments. Let's see. Okay, I think that's all I had about before we start coding, which is going to happen next. That's all I had on the.
Pastor,
Yes.
yeah, I was a little bit confused, lost on the outline. So the outline, is it something you specifically create or is automatic? I didn't get that.
Yes, thanks, Webir. So the outline is going to be made up of 2 components. One of them is going to be your heading levels, right? So all the heading levels here, like one setup, loading packages, or data wrangling, these were things I created myself and share with you all. So it's partially what you create, but also every time we have a new chunk, if that chunk has a title, it shows up on the outline as well. This was one of the options we changed on the first day of class when we went to the global options, if you remember. So it's a combination of both you explicitly creating your heading levels and also placing chunks and naming them. So those 2 things show up on your outline.
Okay.
Awesome. Any other questions? All right, I don't hear anything, so let's get started. So the goal of this exercise is to show you a data frame that has some data that was collected on the field. I'm going to explain to you better what that was, how it was done. In the past, when I taught this, I think my audience was mostly agronomy, crop and soil students. So if you're not from that background, and if I'm saying something that is not clicking to you, is not making sense, let me know. I'll be glad to take a moment and explain a little bit deeper. But this is going to be a agronomy field study example, just so a heads up. So our goal here is to take in this data frame as is, look into some potential issues with it, think about what we have to do to make it in a format, to make it in a final format that is useful for plotting and analysis, okay? And then I'm going to be teaching you some very important and frequently used data wrangling functions to go with that. So as I was telling you, every script, I always start with the first part of it is always loading the package that we need. We have here read Excel is a package to read in our Excel files. We have janitor, which is going to help us to fix and standardize column names. We have dplyr and tidyr, which are two packages that we're going to be using for data wrangling. Dplyr, tidyr, and readr, but we'll talk about later. They're all part of the tidyverse. If you ever hear this term, the tidyverse is a collection of packages where most of them were developed by RStudio, some were not, but they all follow a similar philosophy of coding, a similar way of specifying arguments. This was a huge need in R because before the tidyverse, there were you can still do a same task in 5 different ways or more, right? But the issue is that you may do a task here, a wrangling task that use some functions that you specify things one way. And then when you go to plotting, you use another function from another package that was not developed by the same people, did not have the same mindset when they were being developed, and then now specifying things in a completely different way. So tidyverse is this collection of packages that all serve different purposes, but they were all developed with the same underlying philosophy of how you use the functions and how you specify arguments. So it's easier for us to learn and use. So dplyr, tidyr are the packages for wrangling from the tidyverse family of packages. And then readr is just one other package to export a CSV file. So if you don't have one or more of these packages installed, you already know how to do that. You use the install.packages function. So let's say if I did not have the read Excel, I would just do an install.packages and then read Excel. Remember that after you run this, you want to either comment off so it does not stay active or just delete that line of code altogether because we only install packages once or maybe twice to update it, but we load it every single time. So for now, if you're not sure if you have a package, what I would say is have your cursor in one of these lines and just run one by one and see if it goes through. If you don't have one of these packages, it's going to say package X does not exist or is not installed, something like that. And then you know you need to install first and then load it. Once you know, if you know you have everything loaded or everything installed, you could have just done line by line as I did, or you could just hit the play button and have the whole chunk run at once. All right. Let's move on to our second chunk here, which is where you're going to start actually typing with me. So the goal here is to first import a data frame, right? So, and I want to assign that data frame to this object called soyk. So let's use the assignment symbol. Because the data, let me go back there just to remind you here. I'm going to go to the Files tab. I'll go to the Home folder of the project and go inside Data. It is an Excel file. So different file types will require different functions to be read into R. The function we're going to be using here is called read underscore Excel, right? Because this is an Excel file. If this was a CSV file, we would use read CSV, for example. If it was a TXT file, it would be read TXT and so on. So here, the next thing that we're going to give as an argument for this function is the path to where this file lives in our operating system. So open and close quotation marks. If you hit tab here, this is basically showing you where this script is. So the script, if I just come here inside of code, there's only one file where the script is, which is the script itself. And because of that, it just auto-completed to the name of this file. However, that is not what we're trying to import. We're trying to import the data, which is in a different subfolder. So a really simple yet important concept here is, so right now, our path is inside of the code folder. I have to get outside code and be at the main level of the project, go inside data, and then specify the data file. How do we do that using coding like this instead of clicking ourselves? So whenever we specify a path to get outside of a folder, we use the notation dot dot forward slash. So if you type dot dot forward slash and hit tab with your cursor after the forward slash, you should now be, it should give you the options of what it is seeing at the main level of the project. This is what it should be seeing. If you're working on a Windows PC and you have issues, let me know, because sometimes Windows may be a backward slash instead of a forward slash or some differences like that. So if you have issues, let me know. It could be related to that. But if you get here and now you're seeing the options at the main level of the course, so we need to go inside of the data folder and you can just click on it. It will autocomplete for you. And now if you give another tab, it's gonna autocomplete 01 soybeans because that's the only file in that folder. If there were more files, like sometimes there may be, it's gonna give you a list. You can just click the one you want. All right. So again, this is a relative path. It is relative to where, or in this case, to where this script was. That's the beginning of this. If I share my script and my whole project with you, you will be able to run seamlessly. If I use absolute path to starting at the root of my computer, you would not be able to use seamlessly. You would have to edit the path so it matches on your computer. So a pro of using RStudio projects. All right. If you run this line of code, I'm just gonna have my cursor there and push command return. It should import it for us. So you should see soyk pop up on your environment. And now I left you the code there for us to just print what soyk is right below here so we can visualize that. So it is a table or a data frame that has 16 rows and 8 columns. If you are, and notice how that print of the table was right below this chunk, right? It's not on my console, it's not here as it was within our script. It is right below the chunk. And a couple ways you can use to navigate here if you wish is on the bottom, you can change to the next page. It shows you 10 rows at a time. So you can navigate here to the next rows. If you want to see the remaining columns, you can use this arrow on the top here and just see the remaining columns. This is a very small, very simple data frame. But let's say you have a more complex data frame. It may be tedious for you to be clicking here. One function that I use sometimes is the function view. So if you come here right after that comment and type view, this function could be, the V can be uppercase or lowercase. It does not make a difference in this case specifically, but R is case sensitive otherwise. If you click view soyk, it actually creates a new tab for you with the data frame there, and it perhaps is more like an Excel type of view of this file. All right, so let me introduce you to this study, tell you what it is, what it was, what was collected, and how this was performed. So this is a study where soybeans, so soybeans is one of the major crops, row crops in the US in general. It has its importance in Georgia, and it's grown out on the field, right? So you go out on the field, plant a large area with this crop, and then you have your plots where you apply different treatments. This case here, the study was conducted in 4 locations. So Tifton, Midville, Watkinsville, and Macon. And what this study was, it was a randomized complete block design. That was the experimental design of the study with 4 blocks. And the treatments were different potassium fertilizer rates. So a lot of times, one of the main limiting factors of crop yields is fertilizer. In soybeans, potassium is a very important nutrient, and therefore we have to supplement that. Depending on the soil type, we have to supplement it to improve yields. The goal of this study here was to evaluate the effect of 4 potassium rates. So 0, meaning no fertilizer, 50 pounds of potassium per acre, 100 and 150 pounds of potassium per acre. Those were the treatments. And then they evaluated in 4 different locations. So they repeated this study in 4 different locations in Georgia. And at a specific growth stage, which here is called R4, if that doesn't make sense to you, it's just a reproductive stage of soybeans. So we know when we are in the growth of the plant. So at R4 stage, people went out there and collected soybean leaf samples to assess what was the potassium concentration in the leaves, trying to see if the concentration in the leaves was being affected by how much potassium fertilizer was being applied. So you apply potassium fertilizer and you check how much the plant has actually taken up of that fertilizer by looking at the concentration on the leaves. Okay, so this was the study. It was a field study out on the field. And this is the data we get. So we get the percentage of potassium on soybean leaves for each one of these plots that receive different potassium rates in 4 different locations in Georgia. This is what this study was. I have a little bit of explanation of that here as well, if you want to refer to that afterwards. All right, I want to show you a function here that we have not used yet, and it's a very useful as well to get an idea of your data, which is called glimpse. So the glimpse function comes from the dplyr package, and if we just say glimpse and the name of the object, if you print it, this is what we see. It's kind of similar to the summary function in some ways. So it tells us how many rows it has, how many columns it has. For each one of the columns in this data frame, it is telling us what is the type, how is R interpreting the type of that variable. If you remember, DBL is numeric, CHR is character. So only stage here is being interpreted as character. Everything else is numeric, which makes sense. It should be. Sometimes what may happen, for example, just so you have an idea. So I'm looking here, potassium concentration, Tifton, Midville, Watkinsville, Macon. Everything is double, but Macon is character. And I wonder, this should not be character. It should be numerical. It is a number, right? We want to analyze as a number, not as a letter or a word. So what's going on? This is one way you could check for errors. Sometimes what I've seen is people may want to, so if you have a missing data, an NA on your data, you may be tempted to code that, or to code, what I mean by code is on your Excel when you're typing it, you may be tempted to put a dot instead of just leaving blank. Some people do that. If you do that, just in one cell of that entire column, if you put a dot and everything else are numbers, R is gonna assume that that column is character. So just an example of where this could come in handy. Because if you come here and you see potassium concentration as character, something is going on, you have to fix that before moving on. All right, everything looks okay here, and then it gives you just a few of the initial values of each one of those columns. Something I forgot to explicitly say here, but on your side, on your scripts, if I'm saying something that you want to take note of, you can just write down outside of the chunks, right? You can write down here. Oh, yes, thanks. Thanks for pointing that out. So remember, you can take your own notes anywhere outside of the chunks. Let's see, Comfort has a question. Yes, Comfort.
I wanted to ask that why is the treatment also numeric? Like I know it's 1, 2, 3, but we're gonna like analyze that.
Yes, that's a great question, and we're gonna talk about some of those details next. But that's a great point. So Comfort is asking, why is treatment numerical here? And let me address that right now, as long as addressing some of these column specifications here. Thanks, Comfort. All right, so I guess before we get to Comfort's question, I just want to show you something else. Every time, every single analysis I do, regardless of how complex the data is, I always do some exploratory data analysis, and I do that by using tables and plots. Here, I'm going to show you some tables, right? So, or I guess text output. So the first one is using glimpse. The second one is going to be using summary. We have used the summary function on the intro to R, so you should already be familiar with it. So summary of soy K. If you remember, summary, if the variable is numeric, is going to give you a statistical summary of that entire column. In our case, we just have 16 rows, not that big of a deal. But I have some data frames that we're going to be working in this class that may have thousands of rows. So how do you get a sense of what's in that row if it has too many rows for you to visually be able to assess? Summary is a great option. So for example, here, I know that potassium concentration in leaves of plants, at least row crops, it has a range, right? We would expect it to be maybe between, I don't know, around from 1 to maybe 5%, depending on the crop. So the summary function helps to get a very quick glimpse. I guess I'm mixing the function names when I'm explaining here, but a very quick assessment if there's any error in that column, right? So for example, if my minimum concentration is negative here, that's an error, right? You cannot have negative concentrations. It could be 0 potentially, or very close to 0, but not negative. So if you have a negative value on the minimum, that's a red flag. You have to fix that before I keep moving on, right? Similarly, if this is a percent column, if I have more than 100%, that could be a red flag, right? Hopefully would not have something that's over 100% of any type. In this specific case here, biologically, we know that this should not be more than, I don't know, 6, perhaps. If you have even like a 15 here, that could raise a red flag. Like that is not biologically common to see 15% of potassium in leaves. So maybe you should, look back and see, was that a typing error? Was that an instrumentation error? What happened there? And then make a decision about that point. So summary is really useful for that, checking the minimum, checking the maximum. If you have NAs, they would say here how many NAs you have and so on. So really useful function to have that quick assessment. All right, so now going back to Comfort's question. If you take a look at this data frame, specifically on the column names, the column headings, I want you to pay attention here. So we see a few things that are not very friendly to any programming language. So we see plot with the P uppercase, we see TRT for treatment, everything uppercase, with the stage, everything lowercase. On the K rate, we have a white space, we have special characters like parentheses here, and then we have a lot of white spaces in other columns. Like using uppercase, lowercase is not an issue itself, it's just lack of consistency. But then having white spaces and special characters in column names it's going to cause you trouble. It's going to make it harder for you to use these column names. It's going to potentially create issues on your code. So we want to avoid white spaces and special characters on column headings, okay? Here we just have 8 columns. So maybe you would be tempted to go back to your Excel file and maybe manually edit these column names, so they are easier to work with them in R. However, what you're going to see in this class, I think we're going to have one exercise that we have over 100 columns. If you have inconsistencies like this in many columns, doing this by hand is unreproducible, it's tiring. I mean, you can do it, but it's not the best, right? You're going to get tired very soon. You may make mistakes. You may name something with the wrong name and never know, right? Because you did it directly in Excel. So there are better ways of automating that process. That is the first thing we're going to do here on this chunk. Our first data wrangling step is going to be to standardize the column names of this data set. So if you come here, use the assignment symbol, we're going to use a function called clean_names from the package janitor. This package has many functions that help you standardize column names and do other things to standardize your data. I'm just going to be using this one function that's very useful. So if we just say clean names and then soy K is the first argument here, you're going to notice that for the majority of the functions we use, the first argument is normally the incoming data set or incoming object that you want to do something with it. So that is normally the first argument, right? So if I run this clean names on soy K and I assign the result of that to soy K1 and I just print soy K1 below here, look at what happened. So the default is to make everything lowercase. That is helpful, and let me tell you why. Um, when I read this, I thought, well, this is kind of silly because I don't know if this really makes a huge difference or not. And I never timed myself. But if you have your column names starting with uppercase letters, it is an extra hit that you have to do on your caps lock on off when you're typing that variable name, which is very simple. We don't spend a lot of time on this, but if everything is first letter uppercase, it's just adds a little bit of an extra step that you don't really need it. Your column don't have to be the first letter uppercase. So the default here is to keep everything lowercase. And then notice what happened. So potassium rate was K, white space, rate, white space, parentheses, right? So here it basically replaced the white spaces with underscore and removed the parentheses, the special characters. And it did that across all columns. So it's a very simple way to quickly standardize your column names to a system that is consistent and it's easy to refer to, because now you can easily refer to these columns with underscore. If they had white spaces, you would have to do some extra steps to refer to them when we're plotting, modeling, and so on. So very, very, very useful tool here. Yes, we have a question, Priscilla.
Yes, so my art studio stopped working, so I have to shut it down, and I'm back again, but my Read Excel is not working anymore.
Okay, so when you relaunch your project, did you run the first chunk to load the packages?
Yes, I did.
Okay, so you ran this and the function read Excel worked,
Yeah,
and you're seeing the 02 wrangling on the top right with the project name.
yes,
Hmm.
yes.
So what I would recommend is, and I can do that on my side for everyone to see. Let me just, so I save my script. If you're not having issues, you don't have to do what I'm doing. But Priscilla, if you want to do what I'm going to show, you can do that. I'm going to save my script and I'm going to close RStudio altogether. And then I'm going to navigate back to that 02 wrangling folder. And I'm going to launch RStudio by clicking on the rproj icon. So this is a very, very key concept, simple as well, but very key to make sure you keep yourself following the reproducible workflow. From this point on that we're using RStudio projects, every time you want to work with a given script that is inside of a project, please do not double click on that script. So do not come on code and double click that script and launch RStudio that way. Why is that? As you are accumulating projects, RStudio projects, this may launch on a completely unrelated project. So for me, it did launch the script, but it is on a project none. So this can start causing issues if you just do this without thinking about it. So from this point on that we're using RStudio projects, my recommendation is if I want to work on that script, I launch that project. I launch RStudio by clicking that rproj icon to make sure I'm launching that view and that focus of this project. So Priscilla, I asked you to close RStudio and then asked you to go
Yes.
to wrangling and then launch the project again from the rproj icon. And then try
Okay.
to run things now and see if it works. So try to run the library chunk first, and then you can run just the soy K line and see if that works. Did it work?
Trying it right now.
Okay. Any updates?
No, it's still not working.
Hmm. Does it say anything? Like if you looking on your console, does it say any errors or what's
So I typed the red Excel,
Mhm,
type all the things in parentheses, and
mhm.
it says that, wait, let's see.
I guess so what I would do is I would run the first chunk with all the library functions. And then I would only run the soy K line after that. So if I have my cursor here, I push command return, it just runs that. On my side, I don't get any errors on my console because it worked. If it's not working on your side, then it's probably giving you an error message on your console. What is
This path does not exist.
okay? So if your path does not exist, I think you may have missed a step when we were organizing things. So what I would tell you, did you save the zero on soybeans inside data?
Yes.
So like so I click here on the R blue button. I look at this is the main folder of the project. I'm gonna click on that engine, show folder in new window. If I click on data, you should be seeing zero on soybeans here.
Dr. West says I'm also facing the same problem. Whenever I'm clicking the data, it's not showing I mean, it has the name of the soybean file, but there is no Excel icon at the left side like yours. And it's showing me the same error like path doesn't exist.
Okay, so a quick question here. Ariful and Priscilla, are you using a Windows computer?
Yes.
Yes.
Okay, so I know that on Windows, if I remember well, you may want to try to use a backward slash instead of a forward slash.
Yes, I did that.
You tried that and didn't work?
No.
Hmm. Anyone else here using Windows?
Yeah, I'm using Windows.
Okay,
I'm
Mine
using
is working
Windows
just
too,
fine.
and it's working.
and it's working? Hmm.
Just he's also facing the same issue there like G is a file error. So it's loading the file, but it's not showing me. And only it shows when I click view. So it's loading the file, but not showing it.
Hmm.
When I
Okay.
use the view, so it shows there. Code is running, everything is fine.
But it's not showing soy K on the environment?
Yes.
Is that what's happening with you? But so if you keep running everything else afterwards, it works, even though it says the file was not loaded?
Yes. When we click view, so it shows all the data.
Okay. So Priscilla and Arifo and maybe anyone else having this issue, it seems like there's something going on with Windows that right now I'm not sure if we're gonna be able to solve in class. But so what Arminder and Aitan here in class said is that so he says it doesn't load, it doesn't read, but when they try to print it, it prints. When they try to use it downward, like in other parts of the code, it works. Is that the case for you? Like even though it says it's not reading, does it still work when you try to use that object?
No for me.
Hmm. Okay. So let's
Yeah,
do
me neither.
um, if possible, I try to do troubleshooting in class so other people can see what's going on. And we can always learn something new and some mistakes that we may make and how to fix this. I don't think this is anything you're doing wrong from what you're telling me. It may be some compatibility issue on your specific computers. Let me see, we have a comment here. Oh yeah, yes, Comfort, no problem, thanks. But so what we're gonna do is I'm gonna continue with the code. And then those of you having issues, I apologize, you're not gonna be able to follow before having your side fixed. But I think we may have to connect with Arminder and maybe try to troubleshoot outside of class. So I would ask for you to still code along and still, try to learn what we're doing, even though you're not running on your side. It's still going to be useful to you to see what we're doing, how we're thinking about things. And then afterwards, once we figure out that first step of why you're getting the reading error, then your code will run smoothly. So
Okay, no problem.
all right. Okay, so I guess let me ask this. So Aitan, on your side, you're still able to run after that. Still works?
When I want to print soy cow, one update.
You couldn't. Okay, so we have Aitan here, we have Priscilla and Ariful. So 3 people having issues. Anyone else having issues? So I am aware of it. Okay, so 3 people. Aminder, can you connect with them after class to make sure that we help them to figure this? So yeah, so all the 3 of you having issues, we'll address what's going on your sides later with Aminder outside of class time. All right, so well, I just showed you here. If we come back here, we just use clean names. We got everything lowercase. We got white spaces replaced by underscores, and we got special characters that was the parentheses removed, right? So now our data frame, the columns of our data frame are consistent and easily referable, I guess. Okay, if you come to the next chunk here, I want to show a function called filter. Before we actually do that, I want to show you a quick trick here that I use a lot when I'm doing data wrangling, especially if I have a lot of column names that I may be forgetting what the exact name is that I need. So this function names, if you just run that, oh, I have to create SoyK1. If you just run names here, it's going to show you the name of all the columns available in SoyK1. So, and let me take one step back here to remind you that we took SoyK, the original data frame, we clean names, and we assigned the result to SoyK1. Okay, so remember SoyK1 is the clean named version of SoyK. Now, let's say if for some reason I wanted to filter only certain rows of this data frame that fulfill a certain criteria. I want to, propose here the overall objective of only keeping the rows where the potassium rate that was applied, so the treatment applied, was at a rate of 0. For some reason, I just want to take a look at those rows. How would I do that? So if you come here on SoyK2, let's give it the assignment symbol. We're going to use a function that's called filter. As very common on these functions, the first argument is the data frame coming in. I want that to be SoyK1. Not SoyK, but SoyK1, which is the clean name version. You give it a comma, and then the next argument is what is the condition you want to use to filter, right? I want to break the line here just so it's more readable for us. So what I want to do is I want to filter only potassium rates that are equal to 0. The name of the column is this one, K rate pound per acre. This is our column name. So I give that column name. And the condition is that it equals to 0. So we need to give 2 equal signs, 0. If we run this, and if you had your comma in the right place, you close the parenthesis in the right place, and you print SoyK2, it should only have 4 rows, which are the rows where potassium rate was equal to 0, right? One notation point that's important for you to be aware of is every time you are creating a condition like this that is based on a Boolean operator. If you have not heard about this term before, Boolean operators are equal to, different than, more than, greater than, less than, and so on, right? Those are all Boolean operators. So when we're doing Boolean operators of equality, in this case, you have to give 2 equal signs. 1 equal sign is probably not going to work. Just to give you an example, a slightly different example, if I wanted all the rates except the 0 rate, how do I do different? I could say I want all rates that are different than 0. To give a different here, instead of the first equal sign, you just have an exclamation sign, equal sign. This is the notation for different. So if I do this, if I run that, I should get all rows except the 0 rates. So I get 12 rows here. The data frame had 16 total rows. 4 rows are missing. Those are the ones where potassium rate was equal to 0. Right? We could have used greater than, less than, but this is just an example for you to understand that we use the function. So when we're trying to filter specific rows, I want certain rows of this data set that match a certain criteria. We use the function filter for that. All right. Now let's go to our next chunk. I want to show you here another function that's very useful in data wrangling. That's called mutate. So the function mutate we're going to be using whenever we want to create a new column in this data frame. In this next step of this wrangling workflow, so if you check here, potassium rate is in pounds per acre. That's how the treatments were created. That's how the rates were applied. But now I want to publish this in a paper or maybe in a presentation. I need to use international units, right? So I have to transform this potassium rate from pounds per acre to kilograms per hectare. That's going to be our next step here. So we're going to create a new column that's going to be the potassium rate in kilograms per hectare. How do we do that in this context? So we're going to, whatever we do, we want to assign that to a new object called soy K3, right? So we did soy K1 was clean names. Soy K2 was the filtering. Now soy K3 is our third step. So give it the assignment symbol. We're going to use the function called mutate. The way the mutate works is the first thing we give it, again, is the object coming in. I do want to propose that we use soy K1 instead. If you remember, soy K_1 was the clean version or clean named version. Soy K2, we filtered out some rows just to show you how you would filter rows, but I still want to have all rows moving forward. So we bring in soy K1 at this level, give it a comma. Let's break a line just to make it more readable. The way that this works is you first specify the name of the new column that you're creating. So to keep consistency with the previous name, we're going to use K_rate_KGHA to specify potassium rate in kilograms per hectare. You give one equal sign because it's not a Boolean operation. We're just seeing what this is going to be after that. And then we're going to do a transformation. So the transformation is basically, we need to call the column K_rate pound per acre exactly as it is appearing on the object. And then to transform from pounds per acre to kilograms per hectare, we just multiply those pound per acre values by 0.454 and divide that by 0.405. This is an approximation of that transformation. You can just copy what I just showed you there. So you first multiply and then you divide, and that's how we get to kilograms per hectare, starting at pounds per acre. If you run this and you print soy K3, and you just navigate here on this right arrow to the last column, so the newly created column goes last, this is what we get, right? So 0, 56, 112, and so on. I really don't care about all these decimal points that is showing us here. That's not going to be very friendly when we're creating plots or things of that sort. So I just want to round that number to have no decimal points, just a full integer right there. I'm going to come back to my code above. I'm going to add a comma, here return. I want to say again, potassium rate kilograms per hectare. So I'm basically overwriting on the same column that we created initially for this. I'm going to give one equal sign and use a function called round. So on this function, we say what column we want to round, which is again, K_rate kilograms per hectare. You give it a comma, and then you say how many digits you want to round it to. We're going to say 0 because I want no decimal points. If you run that and you print soy K3 and you navigate to the right to see the last column, now we have our potassium rate in kilograms per hectare with no decimal points. Very easy to read, very friendly to show in plots and tables. All right, so 10:44. Today we're going to 11:30. So I think we can take a quick break here, like a 5-minute break, just to let you stretch your legs, do what you need, and then we'll come back at 10:50 and continue this exercise. I'm gonna set a timer on my phone, and in the meantime, so Priscilla and Ariful, I'm gonna take a look here on Aitan's computer because I think she's having a similar problem and try to help her. If we find out what's going on her side, I'll probably be able to help you as well. So if we find a solution in class, I'll tell you before we come back from the break.
Thank you.
Okay. All right, let's see. Okay, well, I can tell. So Arifu is there. Priscilla, are you there?
Yes.
Yeah.
Okay, so we found out the solution on Iton's computer, and I remember this happening last year as well. For some reason, on Windows computers only, if the actual path to the file is long and if it has white spaces, it may give you issues to read into R. And I think Windows has a limit of how many characters can go into a path before it gives you issues. That could be what's happening on your side. So one thing that that Iton did that worked for her was to decrease the length of some of the folder names. So for example, here I have this, so my class folder has a huge name, right? It's a very long name that you're seeing right here. On her side, I think she just decreased that name to be shorter. So like CRSS 8030, for example. I don't know how it is on your side, if it is long or not, but if it is, shortening the path, I mean, shortening the name of the folders that you're using that are going to be part of that path can help with it. So maybe you could shorten the name of the folder of the class. You could, if you want, once you go into 0 to wrangling and go into the code as well, if you want to shorten this to something that still makes, I would still leave the date and maybe just say like 0114 wrangling, if you want to shorten this a little bit. That could be the solution. Maybe try that out and let me know. Once you do that on your file system, then try to do the read Excel again. Remember to load the packages and then read Excel, and then let me know if that works.
Okay.
So sometimes if read Excel don't work, read that Excel XX works better.
XLSX. Is that a function from the same package?
Yeah.
Let me see. Okay. Yeah, I'm not sure. Well, let's try that first, and then Arifu and Priscilla, let me know if that works. Okay, so it is 10:50. I do want to continue. My goal is to finish this exercise today. We still have a few chunks to go. So I'm gonna keep moving, but Priscilla and Arifo, I think if that doesn't solve the issue for you, let us know, and then Arinder can connect with you later to make sure that we figure this out. All right, that's my timer. Let's go. Okay, so we just created this column with potassium rate in kilograms per hectare. Our next step now, and these, so I want, if this type of data set doesn't fully I mean, it's not something you can fully empathize or relate to. Empathize, you couldn't empathize with data frame. To relate to this data frame, maybe try to think of ways of how similar problems can happen in your specific area, because it's more about the problem than the data set, but this is one example that we can apply. And these problems happen very frequently in many different types of data frames, regardless if it is a soybean potassium study or something else. Okay, so I don't know if you have not worked in R yet, you may not know this, but because this is a randomized complete block design, whenever we run the model for this to analyze this data, we have to have a column where we have the block number, or maybe the wrap number, or something that it tells me what is the block associated with that, because I have to have that column to specify in my model. Right now, if you just quickly take a look here on our latest version, Soy K3, we do not have a column for block. Let me use a view function on Soy K3 just so we can have a broader view of what it contains. So this is what it is right now, everything it has. So this, if you're not used to field research, the answer to this question may not be evident to you. But if you've been working in greenhouse, on fields, on pots, things like that, I think you will be able to help me here. So I don't have a column for block. But do you see any column here that we do have that could be useful, that we could use that column to infer what the block number was?
Yes, maybe the treatment.
Okay, so I had plot and I had treatment. Okay, let's think about that. So who said treatment? Shakir?
There.
Swabir? Swabir, how do you think we could use the treatment column to infer what was the replication number or the block number?
So I think I like when you look at the treatment, it has, since we have 4 replications, we have 4 of the ones and 4 of the twos, 4 of the fours, and 4 of the fives.
Okay, we could do that. That is one way. However, if we go that route, we are assuming that it's block 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, which could be, but what if it's not? Right? Then our assumption does not work if we do that. But I like the way you're thinking. I like your thinking of how we could use this. But, sorry, what's your name again?
Shay.
So Shay said plot, and I'm going to go that direction. We're also making an assumption here, especially if this is not your data set and you don't know how it was conducted. It is an assumption, but if it is your data set and you know how you laid out your plots, normally on field, especially field trials, but other types of trials, if you have blocks or replications and you have plots inside of it, block 1, so all plots inside block 1 are going to be hundreds, like 101, 102, 103. On block 2, on replication 2 is going to be 201, 202, 203. This is a very common practice to do because it helps you to organize yourself when you're collecting data and so on. So assuming this was my study and I knew that I had done that, then we can use the plot information to infer the block information, which we don't have yet a block information. So, not necessarily thinking of coding or programming, but just thinking of like explaining the reason behind this. How could you extract the block information from the plot number? Just using English, plain English. How would you explain that? Maybe Shay, do you have a?
Yeah, I mean, hypothetically, you could do a situation where it says, make a new column if plot number is greater than or equal to 100 or has 100 divisible, and essentially extract it that way.
Perfect.
Something.
Yeah, so Shay was saying, we can create a new column that looks into the plot column and says, if plot number is between this number and that number, then this is block X. And if it's between this other number and that other number, then it's block Y. That is exactly what we're going to do. So that was a really good explanation. But if you did not follow that through, we're basically going to use conditions to say if plot number is between this range of numbers, then they fall inside block 1, for example. So we're going to do that. If you have been using other programming languages, or maybe R, or even maybe Excel, you may have used an if-else function before. So if-else functions work in a way where you say, if this condition is true, then this happens. And if it is false, then this other thing happens. That's basically what an if-else function is. We have if-else functions in R. They are very useful if you have one condition. However, as you start to accumulate conditions, as you start to have more than 2 conditions, it becomes really hard to read that code because you start nesting if else inside if else inside if else, and then it becomes a nightmare. It's difficult to understand what's going on. dplyr has a solution for that, which is a function called case when. So I want to show you how to use that function and how we're going to extract block number from plot with that function. All right, so if you come to SOIK4, let's give it the assignment symbol. We want to create a new column that I want to call wrap. It could have been called block as well. Same meaning in our context. So create a new column. I hope you're thinking mutate. First thing that we say here is the data frame coming in. That is SOIK_3. That's the latest version, the one that we have testing rates in kilograms per hectare. Give it a comma. We're going to create a column called rep. So this is a new column we're creating. So up until this point is very similar to the mutate we used before. But now this rep column is going to take one of 4 values. It's going to be either number 1, 2, 3, or 4 to refer to the block number. And that number is going to come from multiple conditions. So to give those conditions, we're going to use a function called case when. So type case when, and then break your line just to make it more readable for us. So this is how this is going to happen. I want to print SOIK3 above, just so we look again at the data frame. We have this plot column. It is numerical, right? It's important that this is numerical because otherwise the conditions that we're going to specify will not work. So I'm going to come here and I'm going to say the way that, so I'm going to use English language, and we're going to be coding in the coding aspect. So you can kind of connect the thinking to the actual implementation of the code. So the case when, inside case when, the first condition is going to be if plot is greater than 100. Well, let me do this. If plot is greater than 100, then, in the then we specify with a tilde, I want our block to be equals to 1. Okay, so this is the first condition. If plot is greater than 100, then block equals to 1, or sorry, wrap equals to 1. If I just run that and I print SOIK4 and I look at the last column where we have the wrap, what happened here? Everything is coded as block 1, right? The reason for that is because all the plot numbers are greater than 100. So just being greater than 100 is not sufficient. I have to establish an upper boundary here on this condition. To do that, we come back here to the plot greater than 100. We use the AND symbol that is on your above number 7, I guess, on your keyboard. And then I give the other condition, which is plot less than 200. So I'm giving a lower boundary, plot greater than 100, and an upper boundary of plot less than 200. All those conditions where the plot matches these 2 conditions, wrap is going to be equal to 1. If you run this and you print SOIK4 and we navigate to the right, you're going to see now that wherever plot was within the hundreds, wrap is equal to 1, and where it was greater than 200, then it just filled in with NAs, which at this point is what I would expect from this function. However, that's not exactly what we need to fill the other conditions, right? We have 4 blocks, so I just have this fixed for the block number 1. So I'm going to give it a comma at the end of this line and hit return to go to the next row and basically continue the conditions, right? So maybe someone else that has not helped me yet, what would be the next condition that you would create for block or for wrap 2? Maybe somebody that hasn't helped me today yet. Say that again. Okay. Right. Okay. So yeah. So thank you, Usman. So Usman said plot greater than 200 and plot lower than 300 tilde 2. If we let's try that out, see if it works. If we run that and we print and we navigate to the last column, that is exactly what happened. Even though you're not seeing the plot column here to confirm, but I can assure you it is working. You can use a view on SoyK4 if you want, but it is working as specified. So let's just finish these conditions here. I hope that you already got the gist of it, that for the next condition is going to be plot greater than 300 and plot less than 400. This is going to be tilde 3 for block 3. And then lastly, because we only have 4 blocks, we don't have any plot with 500s in the 500s or above. I can just say if plot is greater than 400, then block is 4. So make sure you get all the conditions in. Make sure you remember to use the tilde. Remember to add the commas at the end of each one of these lines, except the last one. And remember to close your parentheses. You should be good to go. If you run that and print it, now I wanna actually use view here, just so we can look at the final results of this operation and have side by side. So, I mean, still not, yeah. Okay, so plot 105, block 1, plot 203, block 2, right? I mean, you're seeing that it is matching what we wanted. And then Swabir, you had an idea of actually using the treatment number, right? So in your case, if we had gone that route and just repeated the sequence 1, 2, 3, 4, 4 times, it would have worked in this case, right? However, we were making the assumption that the information was entered that way. If we use the plot number, I mean, we're still making an assumption that plot numbers were numbered following that scheme that I explained. But I think it's a safer assumption to do the plot than to just assuming it was 1, 2, 3, 4, 1, 2, 3, 4. All right, cool.
Dr. Bessus, how we can write like the first digit will be the block number so that we can save some coding line, I guess.
I'm not sure I understood your question.
Oh, so like it's a three-digit plot ID, so the first digit will be the block number. Can we do that way instead of this one? I mean, how I can write that line. Uh, so what I'm saying is that how I can write the first digit will be the block number instead of going like this, that plot greater than 100.
Oh, I see. So like to basically extract the first digit of the plot number and assign that as the block. Yeah,
Right.
we can do that. So there's a package in R called, I think it's string R, I think is the name of the package. I think this is how the package name is called. It has a lot of really useful functions to extract information from strings or from sequence or from any value really. I think it has, let's see, I don't want to fully develop this because that was not the goal of this exercise, but there are ways to do that. And I think Shay was also saying some other ideas of how to do this, right? So I guess in a nutshell, it's very common that a lot of times there are different ways of doing the same thing, right? And this is just an example, right? You don't have to do it this way. Yeah, so I think it has this function called str extract that we could give the column name. Let me try it. If you all want to type, you can. You don't have to. I'm just going to do a quick trial here. I'm going to do wrap2. So str extract. Oh, I have not loaded the. Yeah, so this function is coming from the package string R. So if you have not installed that, it may not be available to you, but I'm going to quickly try that here. So extract from plot let's see, I think I can just give, yeah, let me see if this works. Okay, it did not work. Oh, okay. So this did not work because plot has to be a character. I can do a quick fix on that. Sorry if I don't mean to make this more complicated for you all. I'm just trying to see if what Ariful was proposing would work. So let me just transform plot the character. Let me call it plot 2 so I don't override. And then here plot 2 as well. Okay, pattern must be a string, not a number. Let me try something quickly here, see if it's. Let me do a vector instead. Yeah, for some reason it's not working. There is a way for sure. I guess I don't want to dive too much deeper into this, but it would be something like this where you use a function that extracts the first position of a column. Yeah, there is a way to do that, but in the interest of time, I'm just going to keep moving. But yeah, thanks, Ariful. That's a good question, and yeah, a good reminder that there are many ways to do different things, and this was just one example. All right, so let me make sure I have soy K4 correctly, and then we're gonna keep moving here. Okay, so next step here, let me just print soy K or view soy K so we can have that view again. So as I was telling you, this was a study that was conducted in 4 locations, right? So we had Tifton, Midville, Watkinsville, and Macon. And let's say whenever I do run an analysis of variance on this data, I do want to have the factor location as part of my data frame, which we do not have yet, right? I have to have a column where I have the location information under that column. Right now, I don't have it yet. So I ask you, where is the location information at this point?
It's in the column variables.
Yes, who said that?
Shakir.
Shakir. Yes, thanks, Shakir. Exactly. So right now, our location information is in the column heading, right? I need to bring that into my data frame so I can use it for modeling, for example. So this is a very common function that you're probably going to be using in data wrangling workflows, which right now the data is in a wide format. So we have many columns with the information of KPCT, for example. I want to bring this into a long format. So what I want to do, and try to imagine here as I'm using my hands to explain to you. So we have 4 columns where I have potassium concentration, right? And they have all the values there for different locations. I want to take all those columns and the values under them and stack them below each other. So we're going to take this data frame from a wide format to a long format, right? So taking all the values and putting them below each other. But now how do I know where those values come from? I'm going to need to have another new column that we don't have yet, where the current column headings are going to be repeated under this new column. So let's say the first 16 values are KPCT from Tifton. I need to have another column saying Tifton, 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 all the way down. And then when I bring the other values from Macon, that same column should now change to say Macon, 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 and so on. So I have all the columns in one, all the values of KPCT in one column, and then another column telling me where they're coming from. So again, going from a wide format to a long format, that's what we're going to do next. So let's do that on this next chunk. We're going to assign the outcome of this to an object called soyk5. So use the assignment symbol there. The name of this function is pivot longer, because we're taking from a wide to a long format. So we're pivoting longer. The name of the data set coming in is the first thing. So that is soyk_4 is the latest version that we worked above. Let's just give it a comma. He returned a few times, and it has many arguments to handle very complex pivot types. But the main ones that we're going to specify here, main arguments, are going to be one that is called names2. So here's where we say this new column that we're creating to place all the current column headings. What's the name of that new column? I want this to be called So in quotation marks, location dot K. Give it a comma, break line again. We're gonna have two new columns in this pivoted data set. We're gonna have a column that where the current column names are gonna go, which is what we specified, and another column where the current values are gonna go, right? So then there is a argument for values too. And then I wanna call that K underscore PCT in parentheses. Give it a comma, break line. The next thing that we want to do here is say which columns we want to pivot longer, because it's not all of those, it's just four, right? It's the four ones that have the potassium concentration in four different locations. So it has an argument called cols that was where it specify which columns we want to use. We could use here the C function and specify all the name of the columns very easily. I want to show you a little. So whenever I can, I try to use some different tricks that you haven't seen yet, at least not in my class. This is going to be one of those examples. So if we just print soy K, just to see again what soy K looks like. The four columns that we want to pivot longer are Tifton KPCT, Midview KPCT, Macon KPCT, Watkinsville KPCT. As you may have noticed, they all have this pattern of containing the strings K underscore PCT. And none of the other columns that we do not want to pivot have this pattern, right? So we can use this pattern to, instead of specifying all their four names here, we can give a pattern of the columns we want to select, which is this pattern. So we need to use a function that is called contains. And then here we just give what is the pattern, which is K underscore PCT. If you got all that right, if you got the quotation marks, the commas, everything right, and you run it, it should go through with no issues. And if you print soy K, let me actually view soy K, so it's easier. So now, well, if you remember soy K4, let me print soy K4, it had 16 rows. Soy K5 should have 4 times that. It has 64 rows, right? Because we took 4 rows, or I'm sorry, we took 4 columns of 16 rows and stacked them below each other. So we basically multiply by 4 the total number of rows. And then if you look at the end now, we have a new column called location.k, which is where it placed all the previous column headings. And we have a new column called KPCT where it placed all the previous values, right? So now, even though it's not the sharpest looking, the nicest looking, but we do have a column where we have the location name there, right? So this is the beginning of, okay, we're going to have this column and we're going to be able to use it for plotting, for example. Imagine that now we were doing a ggplot and I wanted to color the points according to location. Now I have something, right? I have a column I can specify. All right, so let's keep going. We have a few more chunks here to get through, and I think these are a little bit simpler as well. So the next one is, there are different ways. So my goal, my final goal on this location column is to just say Tifton. I don't really care if, I mean, I don't want to have a plot where the legend says Tifton KPCT, because that makes no sense. I just want to say Tifton, right? Because the location.
Excuse me, Dr. Bastos.
Yes.
Yeah, I have a question. So in this current chunk, what's the function of values to? What is it doing here?
So values two is just telling that after pivoting, what's going to be the column name under which the values will be stored. So this KPCT is this.
But okay, yeah,
And
I see it. Thanks.
this location K is the name of the new column where the names are going to be stored. So this is where it is.
Oh, so it made 2 columns, one for the names and one for the values.
Yes, that's exactly right. So it took 4
Thank-
columns and summarized them into 2 basically, but 2 new ones that we did not have before. And here I'm just specifying how I want them to be named. Awesome.
Got it. Thank you.
All right, so now the next goal here is I really don't care about KPCT. I just want to keep the location name. There are different ways of doing this, and maybe there are more efficient ways of doing this, but I wanted to show you here a function that is very useful in this case, in other cases as well, which is the function called separate. So now I want to just extract the location name and basically remove KPCT. If you come here to soy K6, we're going to give it the assignment symbol. We're going to use the separate function. The first argument, as always, is the incoming data frame. So soy K underscore 5. Oops, soy. Give it a comma, break line. We're going to tell it the next argument is going to be what is the column that I want to separate its values. So the column we want to separate is location.k without quotation marks. And then give it a comma. Let's break line again. And what I want to do here is use the fact that there is a underline, an underscore here as the character that's been used to separate three pieces here. So if you think about it, for all the values under location K, you have location underscore K underscore PCT, right? So the underscore is the pattern that we're going to use to separate this. And if we separate using that, we're going to end up with three pieces. The first piece, which is going to be location name. The second piece, that's K. The third piece, that's PCT. So because we're creating three new columns, we need to name them, what we want them to be in this coming data set. So there is an argument called into, where we use a C function to tell what is the name of the new three columns that are going to house those three pieces that right now are all together. So I want the first column to be called location. Give it a comma. The second to be called K. Give it a comma. The third to be called PCT. I'll give you a quick moment here to catch up. And let's run it. So I'm going to print it just so you see what happened here. So notice that we don't have the location K column anymore in soy K6. That disappeared. Now we have three new columns. One that is location, one that is K, one that is PCT. They're appearing right here. Location, K, and then PCT is the last one. So really, K and PCT are the same value throughout. They're really not useful for us. It's just that we had to separate them. But the really interesting column for us is location, right? Now we have a column that says location and has the clean name of those locations. So now we can easily use this for plotting, for analysis, and so on. Yes. We could. Yeah, so there are different ways as well. Again, because we're working with strings, that string R package has some great functions that we could just extract the first. So we give it a pattern as well and say we want to extract the first component of that. So there are different ways for sure. Yeah. I guess here I was just trying to teach two concepts. One of the separate and then the concept of select, which we're going to do next. All right. So I think we're basically. Yeah. Mm-hmm.
It's showing like I'm putting that comma of the location dot K, but it is showing some error.
So can you tell me what the error says?
Error unexpected comma.
Yeah, so I think the case here was missing the C function. So make sure you wrap those three locations in the C function. Anyone else having issues? All right, I'm gonna keep moving. Okay, so I wanna show you a function here that is helpful for you to perhaps only keep the columns you want to keep and not have a whole bunch of columns that are useless for you, which is the function select. So a very key distinction here. If you are subsetting rows, you're using the function filter. If you're subsetting columns, and what I mean by that is I only want these columns, but not those, you're using the function select. So filter applies to rows, select applies to columns. So if we just look into the names here of soy K, I'm just gonna run that. And we just think of what are the columns that we really need to keep on with this analysis. So, I mean, we could make different decisions here depending on which way we argument, but I would argue that or which way we argue, but I would argue that we really need location, rep, potassium rate in kilograms per hectare, which is our treatment, and then KPCT, which is our response variable. Those are the minimum ones, right? If we look at soy K6, which is what the latest version right now, plot number at this stage, we really don't need it anymore. Treatment, we really don't need that treatment number because it's just repeating, it's the same information. I mean, it's not same information, but it's the same equivalency to potassium rate kilograms per hectare, right? So all the 0 potassium rates are treatment 1. All the 50 potassium rate is treatment 2. And is really using treatment 1, 2, and 3 is not very useful in analysis. I want to know the actual rate. So we really don't need TRT. Stage, was it just one crop stage? We also don't need that. Pounds per acre, potassium rate. If we're doing this for a conference, we're not going to need that. So really it's just the treatment, potassium rate, kilograms per hectare, the block information or the rep, the location, and then KPCT, which is our response variable, right? Those are the ones that we need. So let's just select those columns before we keep moving. Let's do that here on this object soy K7. So we're going to use a function called select for that. As always, we say what's the incoming data frame, that is soy K_6, give it a comma, and now you don't have to use the C function, you can just specify what are the column names you want to keep. And if you want to change the order, you can change the order here, and that's going to match on the outcome. So I want to have location, comma rep, comma K rate, KGHA, and KPCT, which is our response variable. If you run that and you print it, now we still have our 64 rows after we pivoted longer, but then we only have 4 columns, which are really the ones we need. So select works on columns. Something to help you on your journey learning R is if you load a package, you have access to those functions and you can just call the function name as we've been doing with all these functions. The select function specifically is a function that is very common across different packages. So what has happened to me in the past is I load a couple packages on the top that both have a select function. And then when I come to my data wrangling, I'm doing everything right. I'm trying to select some columns and it gives me an error. It keeps giving me an error that makes no sense. And I'm looking at my code, it looks right. And then I realized that what was going on is that I was actually using the select function, but it was coming from a different package, which was not used for this purpose, which did not expect the same arguments, and therefore was not working. So in the case of the select function specifically, I encourage, there's different ways of doing this, but I encourage that you specifically say which package you want this function to be coming from, just to avoid your issues in the future if you ever run into similar issues as I did. To do that, is explicitly say what package you want a function to come from. You type in the package name, which in this case is dplyr. You use the : notation, and then the function name. So this is saying I want select function from the dplyr package. Just want to show you this quick trick because you may run into this issue in the future, and this may be the solution. All right, so another function here that is really just for visual aesthetics, I guess, of how we visualize data frame is I want to sort a column here based on location. So right now, if you see the first value here is coming from Tifton, the second Midville, Watkinsville, Macon, and then it repeats that. I just want all of them sorted by location. So I have all the Tifton values first, and then, you know, alphabetically sorted with location being the variable for that. So we're going to use the function arrange on this next chunk. You can just give it the assignment symbol. We're going to call arrange. The incoming data frame is the soy K _7 or _7. And then we're just going to say, what is the column we want to arrange by? I want to arrange by location. So I'm just going to put location there. If you run it and you print it, we still have the same number of rows, still have the same number of columns. It's just that our data now has been sorted by location. So alphabetically, that's why Macon is first. So all of the Macon values first, and then the other locations after that, Midville, Tifton, and Watkinsville. All right. Well, I don't think we're going to be able to finish today, but maybe we can do this one more chunk and then stop here. So a very popular and something you're going to use a lot function, or maybe set of functions, is going to be if you want to extract the summary of something on this data set. I want to know the mean potassium percentage across the whole data set, or maybe not across the whole data set, but within different groups of this data set. To do that, we're going to use this combo of group by and summarize. This is a very popular combo that you're going to be using whenever you want a summary over certain groups in your data frame. So let's start that with soy K9. Soy K9, give it the assignment symbol. We're going to start off with the function group by, and then we say what's the data frame in there. That's soy K underscore 8. That's the one that we just created above with where we arranged by location. And then the variable, so let's say I want to get the mean at each location. I need to say that I want to group by the location column. So after saying the data frame name, we just say what's the column name we want to group by, which is location. All right, so if we run soy K9 and we printed, well, we still have 64 rows, still have 4 columns. Doesn't seem like anything changed really. And that is by design, that's by default. Because we just created the grouping within the data frame, and you can see now that you have this tag here of groups by location 4. Soy K8 does not say that. If you print soy K8, it does not have the grouping here. But if I print soy K9, which has been grouped by location, I do have that structure. So group by basically creates this structure that you want to group by kind of behind the scenes. You're not seeing the effect yet of what it's going to do. And that's why group by is used in a combo with the summarize function. So after we group by a certain variable, it could be other variable. It doesn't have to be location. This is just the example. Then we apply the summarize function. So if we come to soy K10, let's give it the assignment symbol. I want to call the summarize function. We need to bring in the grouped by data frame, which is soy K9. Oops, soy K9. Let's give it a comma. I want to extract the mean and assign that to a new column called mean underscore PCT. So we first say, what's the name where this summary is going to go? I say equals to, and then we call the function mean. And because I want the mean of potassium concentration, those values are under a column named KPCT in our data frame. So the mean of KPCT. If you run this and you print soy K10, we have 4 values only. So we went from 64 to 4. That's because each location has a row, and then we have the mean potassium concentration across all treatments and all reps for that location only. Right? And again, we have 4 rows because we have 4 locations, and we group by location. So that's why we have those 4 rows, and we have location showing up there. Now, a quick example here of why doing the group by first is important. If I have not used the group by first, which is basically what soy K is, right? So soy K is right before we group by. So if here on the summarize, if I give soy K 8 instead of soy K 9, and we summarize, we get a single value across the entire data frame. So by grouping by first, you're telling it, okay, I want the mean, but I want the mean by these groups that are under this column, right? So that's why soy K9 did was creating that grouping for us, and then we're getting the mean by each location. Okay, I think this is a good stopping point. We have a very important concept here to learn that I do not want to rush through, which is going to be the use of the pipe. If you have not used the pipe, this is going to really teach you and show you another very important tool when programming in R specifically. And another reason why, I mean, one of the reasons, of course, R and Python, each one have their own strengths and weaknesses. This is, I think, is one of the strengths that exists in R is that the fact you can pipe things together is not making sense for you right now. It will in the next class, but I don't think Python has such an elegant way of doing this, at least not quite yet. You had a,
And it's not to us.
yes, attendance.
Like, it is, you-
Okay, awesome. Thanks, Arminder. Yeah, so before you go, make sure you claim attendance. Arminder just opened an attendance for today on GitHub. Make sure you claim your attendance. And also quick, wanted to let you know. So next class, I'm not gonna be here. My plan is to I will share the video that finishes this exercise with you, and I want to ask you to go through that on your own before next class. And then during next class, we're basically going to start off with Git and GitHub. Amrinder is going to be here to help you out with that. He's going to also open Zoom for those online. And so we're basically going to start working with Git and GitHub on Tuesday. Well, first we're going to finish this exercise. No, erase that. You're going to finish this exercise at home before class. I'll send you the video that continues this exercise to the end. You finish that on your side, on your own. There is a quick assignment there. It's going to be very simple, but you're going to have to do that before next class. And then in class, Aminder is going to show you, walk you through working with Git and GitHub and get those connected next Tuesday. All right, thanks everyone. If you have any questions, I'll stay around for a few minutes. If you don't have any questions, please make sure you respond to GitHub to claim your attendance.